Hi all, my name's Camilla. I am Engagement Officer with the On-Farm Carbon Advice team. And this is our webinar series just to bring you some of the research that's happening within DPIRD or New South Wales DPIRD, should specify that. Today we have Lucas van Swieten and he will be presenting on biochar. Now, before we begin, I would like to acknowledge the traditional custodians of the lands and waters in which we all gather today. I am personally on Wiradjuri country, based near Orange, and recognise their continuing connection to land, water and community. We pay our respects to elders past, present and emerging, and extend that respect to all Indigenous peoples here today. If you'd like to in the chat put where you're coming from, we'd love to hear from you. So today's session will be recorded and will be made available on our website along with all the other webinars in the series. If you have any questions, feel free to put them in the chat and we will open the floor up at the end of the presentation for a conversation with Lucas. Also, there will be a survey at the end of this webinar just to collect your feedback about how the session went and how we can do better next time. So on that note, I would like to introduce Lucas. So Lucas is Senior Principal Research Scientist with the New South Wales DPIRD, and he has been with the department for the past 30 years. He's also Program Leader with the Soil CRC, focused on driving soil resilience and productivity. His research focuses on carbon and nitrogen cycling and the role of recycled organics, unraveling soil, rhizosphere and microbial processes, and the risk and fate of agricultural chemicals. So, Lucas, over to you. Tell us about biochar.
Thank you very much. So I've got a little bit over half an hour to give you a story that probably in reality should take about 5 hours to give. So it's a bit of a snapshot. I've got some science in the presentation today and a little bit of a practical outcome stuff as well. So yeah, please, I'm looking forward to some questions at the end. Line them up and we'll go from there. Okay. So biochar. So I've been personally working on biochar for the last 20 odd years, amongst sort of the first researchers working in this topic. And we've got some of the very early publications, science publications in the area. But I guess the original interest in biochar originated from these terra preta soils. So the top two soil pits that you can see, that's an oxysol in the Brazilian Amazon. And on the right is a terra preta soil developed on exactly the same soil profile. And these soils were developed somewhere between 1,000 and 2,000 years ago, where cooking charcoal and pottery charcoal was added to their farming plots over several hundred years. And these soils have existed and have actually been highly productive since the last 1,000 years, since they were developed. And I guess that got a lot of soil scientists, in particular those from Cornell University, Johannes Lehmann, a close colleague of mine, really interested in what processes are going on. Why are these charcoal amended soils dark? Why are they, even today, highly sought after? Why are they productive? Why do they hold more water? Why do they have less constraints? A whole range of questions came out of it. Interestingly, the bottom two, they're actually taken along the Murray. So it's a sandy soil, yeah, moderately sandy soil. We also had quite a few chrome soils in that area. And Adriana Downey and I published a nice paper on Terra Preta australis a long time ago, back in 2011. And these soils were also generated from charcoal addition to soils. So what is biochar? So the top two photographs are just pictures of a biochar that we made. The one on the left-hand side is a cereal straw. The one on the right-hand side is a poultry litter biochar. And down below are some scanning electron micrographs of these materials. And you can see that the main thing is that they're vastly different. And I guess throughout the theme of this presentation is biochar ain't biochar. There are literally an infinite array of properties that can be had with the biochar. And that depends on quite a number of factors, in particular, what they're made from. This example is the feedstock, the temperature that they're made at, the residence time that they're in a pyrolysis kiln, pre-treatment, post-treatment, and I'll go through some of the later concepts around re-engineering these platform materials for specific purposes. So the main thing here is that there's no such thing as biochar. It really has to be plural biochars. And this has caused some issues with regulation previously. It's not a single product. It's a multifaceted product. So biochars are generally made in a process called pyrolysis, but they can also be made through cold fire. They can also be made through gasification. It's really a continuum of heat and temperature, thermal processing and temperature. And an important point to note here is that it can happen at multiple scales. We've got little cook stoves that are commonly used in South America and in Africa, where wood pellets are fed in, and these pellets burn very, very cleanly, very hot, or they pyrolyze, and they get some biochar out of the process, and they can use it for cooking, all the way through to some quite well-engineered systems where they're producing energy, and that energy that's produced from the system can be thermal energy. So you've got heat that can be used for a range of purposes. You've got heat energy that can be used to make steam. You've got gases that can be directly combusted in a diesel generator or in a gas turbine to make electricity. So yeah, there are a range of scales, everything, as I mentioned, from these small cook stoves through to large engineered systems. And here I've just got an example. This is hot off the press. This particular unit is currently operating in Norway, and it is treating pellets, wood pellets. So there are mountains of old waste wood pellets. Is treating between 500 kilos to a ton an hour of wood pellets, making biochar, and there's some energy capture. I understand this unit itself is made in China, but the important point to note is that it's Australian designed, and here we can look inside the kiln. That'll do. I think you'll all get the picture there, but yeah, these units are in operation. There are some similar types of units in operation in Australia at the moment as well. Okay, so what's biochar made up of? So it's this black stuff. Okay, so we look at plant material, or it could be animal matter. Basically, you can pyrolyze anything that once lived. So you've got plant material that will be made up of carbohydrates, might be complex carbohydrates, might be lignin. The principal components within these are carbon, hydrogen, and oxygen. During the pyrolysis process, you're actually driving off a lot of that hydrogen, a lot of that oxygen, and the hydrogen, for example, will be driven off in the syngas, which is a product of pyrolysis, as H2. Which can then also be separated in some engineered systems to collect the hydrogen. So there's potential for this technology in some very highly engineered newer systems to actually generate hydrogen gas, pure hydrogen gas from the system. But the other gases that come off are methane, CH4, and carbon monoxide, CO, all flammable gases in that syngas category. But the main point to note is that the pyrolysis process tends to leave the carbon, or much of the carbon, behind, driving off the oxygen and hydrogen. Then you've got these other components that might sit in there with it. So for example, if you're pyrolyzing, it might be poultry litter. We know that poultry litter is full of nitrogen from the urea and the uric acid from the feces from the chickens. You've got phosphorus, you've got potassium, you've got all sorts of other minerals that might be present. Importantly, Most of these minerals remain in the biochar. Sorry, I've got the fire alarm going in the background. Great timing. I believe it's a drill. There we go. It's gone off already, so that's good. Sorry about that. Um, so yeah, most of these minerals, in particular, the phosphorus and the potassium and the calcium, remain in the biochar. Some of the nitrogen is driven off. It might be volatilized in the process. But what's important to note here is that if we're putting in contaminated feedstock, it might be contaminated by lead or by zinc. Uh, those metals will come through as well. So we need to remember that sometimes what you put in is what you get out. It's a bit like a compost system. One of the real benefits, and I think a lot of the research now on biochar is around how we can treat some of these complex waste products. So, for example, it might be biosolids that have got PFAS contamination, that might have microplastic contamination in them. How does a pyrolysis process deal with that? And it's actually been shown to be highly effective in the destruction of plastics and microplastics. And it's also been shown to be very effective at removing some of these more forever chemicals, as you know, the PFAS, PFOS type chemicals from the feedstock as well. So there is actually a really nice remediation tool for contaminated materials. So the structure of biochar really depends on the temperature that it's made at. And here we can see a nice diagram that Adriana Downey did many years ago. When materials heated to very high temperatures in the absence of oxygen, you get these sort of graphitic, very ordered layers of carbon. And at the lower temperature, sort of the 400 to 500 degrees, which is where most of the pyrolysis systems are sitting at, you get this more sort of amorphous carbon. You get these aromatic structures, but they tend to be less ordered. Generally, the more ordered the carbon structure, the more stable the material. So these graphite materials will last millennia, if not longer, in an environment. Whereas these more amorphous, less well-structured materials, which are more typical of biochars, tend to have a residence time in soil of between 50 and 1,000 years. So it again depends very much upon temperature, the feedstock that went in to make it, and also the processing conditions itself. But in general, the majority of biochars are made at sort of that 400 to 600 degrees, and the wealth of literature showing that when these biochars are put into soil, they'll last usually more than 100 years and usually less than 1,000 years. So sort of in that range, which is important for the carbon certification and that carbon value. What's also important to note here is that temperature impacts things like surface area on the biochar. So generally, the higher the temperature of the chars, the greater the surface area. And this is important. So we're particularly interested in surface area and the porosity of chars for re-engineering these materials. So for example, if we've got a char made from cereal straw, now we're interested in having a good porosity and good surface area so that we can modify it. We're using it now as a platform material for building particular amendments. Some of the early work, and this was by Lynn McDonald at CSIRO, again, probably 15 years ago now, where we had a look at, I think, 80 or 90 different char materials made through several different processes. And basically what we developed from this is an understanding around the types of properties that biochars have when they're made from different materials. And we had a look at biochars made from grass and cereal, from wood, from manures, and from green waste. So that's probably more like the council compost type material. And if you go to the little sort of principal component diagram on the right hand side, what you'll see is that these wood waste materials and the green waste materials tend to have a high carbon content, and that tends to be their principal property. If we want to have a look more at the manure type materials, it might be food waste, it might be biosolids, it might be poultry litter. We tend to have a lot more mineral matter, as we'd expect, because the feedstocks themselves have got a lot more nitrogen and magnesium and sulfur and phosphorus in it. We've also worked out which types of biochars will have a better liming value. So some of these products have got a pH of 9, for example, but importantly, their liming value, for example, um, paper pulp mill waste. One of the biochars had a liming value of 35% that of ag lime. So the product itself, while being a biochar and full of stable carbon, is also a very useful liming agent for acid soils. So yeah, we've got, I think now in the literature, a really strong understanding of the types of biochar properties that you get from different processing conditions and different feedstocks that go into it. And this is a bit of where we see the biochar cycle sitting in a circular economy. So, for example, you might have a waste residue. It might be cereal straw, it might be sugarcane trash, it might be manures, it might be abattoir waste, whatever. These products can be pyrolyzed. From that, we can get energy. That energy can be utilized in a range of different ways. It can be used to dry materials. It can be used in a processing situation, in a cotton gin, for example, where thermal energy might be needed, um, or to dry grains, or to put electricity back into the grid, or to collect pure hydrogen. We then generate biochar. That biochar can then be put back into the agricultural system. It can be used to improve soil. It can be used to increase the carbon content of soil, um, theoretically improving plant production, plant biomass. Therefore, we get more residue, more cereal straw, which can then go back to the pyrolysis system. So it's a very, very neat, overly simplified diagram here, but it basically just gives, I think, a bit of an understanding of where biochar sits in a circular economy. And some of the reasons that you pyrolyze biomass, and I think I might have mentioned it before, a lot of our landfills are filling up. I think half of our organic residues, I think the 2024 survey showed that half of our organic residues are still ending up in landfill. And a reason for that is many of these have got things like plastic contamination, and that plastic contamination at the top is not a problem in a pyrolysis process. Plastic is like any other material containing carbon, hydrogen, oxygen. It will pyrolyze, it will reform into biochar, it will produce energy. A caveat to that are some of the more contaminated plastics like PVC, polyvinyl chloride, where you've now got precursors for things like dioxin formation. So we need to be a little bit careful with that, but the majority of the polyethylene type plastics, no problem. But the reasons you pyrolyze biomass is biosecurity. So when a material's been heated at 500 degrees, biosecurity issues, seed residues, etc., gone. The material doesn't smell. Biochar is odorless. And in fact, many of you listening would probably have charcoal filters for your water. There's no difference really between biochar and charcoal, other than the fact that charcoal has got some more specific characteristics with regards to surface area. Pyrolyzing it can reduce transport costs, so we're not transporting water. We've condensed the carbon down to about half the volume and half the weight. So yeah, transport costs. We've got beneficial agricultural reuse, which is where we're particularly interested in. You can pyrolyze biomass to generate energy. We stabilize carbon, as we've already mentioned. And there's also the opportunities to lower emissions of greenhouse gases. So Annette Cowie's team at DPI at Armidale and at UNE did some work on composting of poultry litter previously, and have shown that biochar added into compost can actually significantly lower emissions of nitrous oxide. Likewise, it's another opportunity to better manage piles of manure, for example. Let's pyrolyze it. Let's minimize opportunities for greenhouse gas emissions from manure management. Okay, so one of the reasons that we're particularly interested in biochar is that just about all of our agricultural soils in Australia have got some constraint. There's something stopping them from performing at their optimum. And I guess three of the key constraints that most people online here would be familiar with would be soils that are sodic, soils that are highly acid, and soils that suffer from salinity, from high EC. And estimates are around about nearly $2 billion in lost agricultural productivity in the grains industry alone, from these soil constraints. So I guess what we're working on now is how can we use biochar to address these particular constraints. And I think there's some great research and great engineering and technology development happening right at the moment. And I think many of these constraints can be very effectively dealt with some of these newer engineered biochar products. So in Australia, the key chemical constraints tend to be acidicity and then acidity, as I mentioned before, and that's particularly associated with aluminium and manganese toxicity. You've got alkalinity. So some of the soils, for example, on the Eyre Peninsula might be pH 9. At what point you start getting sodium carbonate and bicarbonate toxicity. You've got vast areas of salinity, acid sulfate soils. You've got non-wetting soils. I've got a nice photo of a non-wetting soil coming up, and some agrochemical toxicity. Other constraints include soil structure. So for example, you might have a very heart-setting soil that's compacted. Those heart-setting soils tend to have poor seed germination. They tend to have more surface runoff of water and less infiltration, and that then causes erosion. So we might have extreme saturated hydraulic conductivity, so it might be too high, so the water goes through the soil too quickly, or it might be too slow and it sits on the surface, and then you start getting surface runoff of water. And also some soils tend to have very poor water retention. And then we've also got the biological constraints, which could include disease, declining soil organic matter. And with that declining soil organic matter, it means that we're getting less nutrient cycling, less mineralized nitrogen, less mineralized phosphorus being available into soil, and also inhibition of things like biological nitrogen fixation. So yeah, we've got quite a few biological constraints as well that we're dealing with. This is just an example of what a dispersive soil does. So along the bottom, we've got some examples of adding gypsum to a dispersive soil, and we can see it aggregating. When it doesn't aggregate, it disperses, and you also get slaking. And we can see an example here, a photo from Victoria, where we get water on the surface of the soil rather than infiltrating and being stored in the soil. So soil acidity is a real issue. And one of the things that we're trying to fix up in sodic soils is around the bucket size, how much water is available for the crop roots. So this is an example of, and I won't spend too long on it because I could spend half an hour talking about this particular topic, but this is an example of a sodic soil and the available water throughout the profile down to a meter. And that area sort of shaded in red or pink is where we've got a sodic subsoil constraint. And that area is now soil water that's actually not available to the plant. If we could fix up that constraint, it means that we've got a lot more plant available water at 40 to 90 centimeters in the soil profile. And that could have significant ramifications in dry years, or potentially those decile 2, 3, 4 years, drought years, in other terms, where plant water is inhibiting crop yield. And I think there's some great opportunities there. And we've got trials on at the moment where we're addressing these subsoil constraints. Some of these dispersive soils can end up with crusted layers, with heart-setting layers that honestly are like concrete on the surface. When these soils dry out, they become rock hard. We've got some great work again where we're showing that we've got biochar in that particular system, in that surface soil. We're getting lower bulk density because biochar itself is it's a very strong but very light material. It lowers the bulk density. It now helps to start developing aggregation and pores, and we tend to have a lot less heart-setting issues where we've got biochar in those systems. And this is a great example of a non-wetting sand. So many of you probably have had pot plants in the past where you water it and the water just drains straight down into the pan at the bottom and the soil feels dry. That's actually generally a microbial outcome, where once the soil dries out or the potting mix dries out, the microbes develop form waxes, for example, and those waxes are designed to protect them, to keep the moisture inside their spores, to stop desiccation. But that also then causes this as an outcome. These waxes then become water repellent, and it's actually quite hard to get water into that system. And that causes a whole range of agricultural issues. And I think there's some great examples here where these soils amended with biochar can hold water for a longer period of time. You tend to get a bit more microbial activity when water is available, and these waxes tend to be less of an issue. And I mentioned before, we've got these alkaline soils. So it might be a silicon-based sand or a carbonate-based sand. And yeah, these particular soils have got, as I mentioned previously, a range of constraints. And the main one here in this particular soil, thanks to Dave Davenport for that photo, is around phosphorus availability. So on this soil, you add your superphosphate with your crop, and the calcium in the system ties up that phosphate very, very quickly. And generally, most of your crops tend to be highly phosphorus deficient. And I've got some examples of a product coming up. And declining soil organic matter. So, as I mentioned previously, organic matter is a resource of nitrogen, phosphorus, sulfur, potassium, charge density. So it develops cation exchange, anion exchange. Organic matter is really important for as a microbial food, as a water store, and it buffers against environmental fluctuations. Most of Australia's soils tend to have declining soil organic matter. The whole process of cropping or agriculture actually generally results in lower soil organic matter. There are some farming techniques that have definitely minimized the rate of loss. For example, no-till, I think, is the classic example. But many farmers now are looking at some techniques like cover cropping, application of organic amendments, for example, stubble retention, that can either slow or possibly reverse some of those organic matter declines. But this is a really important area where biochar can fit in as a solution. So in a nutshell, I think what's really important here is that we need to understand soil to better manage the soil. So it's critical to understand what constraints you have. And this goes particularly with understanding where biochar might fit into that system. So I've seen so many cases of researchers and farmers getting some biochar, chucking it into their soil, not really knowing what it's going to do, and nothing happens. And you go, well, what were you trying to fix up? I don't know. I just thought biochar was good for your soil. You'll get an increase in carbon, yes, but you won't necessarily see an environmental outcome. So, for example, a biochar that you might use in an acid soil will actually have a detrimental impact when it's applied into a calcareous soil, and vice versa. So you really need to understand what properties of the char you're trying to achieve to get a particular outcome. Likewise, a biochar that we might design for that heart setting soil, it might be a wood waste biochar with very little nutrient value, but it's just going to be very light, large pieces, large particles. But we know it's going to lower the bulk density. We know it's going to increase water infiltration. It's probably going to do nothing in an acid soil, but it's going to be very useful in that heart setting soil. So we need to understand the constraint to understand what property of biochar we're going to deliver to address that constraint. And then, yeah, it's the same with any input. This is just an example of why you might add lime, why you might add fertilizer, why you might add something to lower sodicity issues or salinity issues. Is really just understanding what are the constraints before you try and fix them up. And again, this is critical for biochar research. Okay, so a lot of the work sort of in the last 5 years, maybe even stretching out to 10 years, is around re-engineering biochar into what we call these sort of carbon composites for addressing particular constraints. So this field trial was set up in Lockhart in southern New South Wales. We can see a picture of that field trial in the bottom right hand corner. It's a very sodic soil. We've got an ESP of, I don't know, 15 odd percent at 40 centimeters depth. And these amendments were designed to be applied subsoil using that piece of equipment as a deep ripper with a chute down the back, and it's delivering these amendments sort of in that sort of 20 to 40 centimeter range. And they're getting some very positive feedback from that work around improved yield, around improved soil water uptake from depth. So again, designing these organic amendments, these biochar containing organic amendments for that particular constraint. Here's another example of an engineered product that was designed by the New South Wales DPERD team for use in another soil CRC project. And this work is courtesy of Nigel Wilhelm at Sardi on that calcareous soil. And we can see on the right-hand side, typical practice, and on the right-hand side of that photograph, this engineered biochar. So we've got matched phosphorus content between the typical practice, so your single super going out, and the same phosphorus going out in the biochar on the right-hand side, and very, very significant improvements in crop productivity from that particular product. So we're actually currently talking about potential commercialization options for that as a novel fertilizer product. And yeah, does biochar impact yield? So we've got some examples here of these engineered biochars designed for a specific purpose, having very significant impacts in yield. But what about just straight biochar? And this work has come out of Marta Camps's group in New Zealand, where they did a meta-analysis. So they just collected 200 scientific papers from the literature, and they had a look at a range of factors around what is it about biochar that impacts crop productivity. And it would go along the left-hand side, things like the rate of fertilizer application, how much biochar do you add? Do you add 5 tons or 20 tons? The soil that was put into, like, was it a sandy soil or a clay soil? What's the cation exchange capacity of that soil? That tends to be an important one. What's the biochar made out of? And also, what temperature is the biochar made at? And the graph itself, so we've got that line up the middle, that sort of the 0 mark. And then we've got all these sort of bar charts going across. And we might see, for example, in red, we've got the cereal straw feedstock. There were 75 studies showing that on average, we were getting about a 24% increase in crop yield when cereal straw biochar was added into cropping scenarios across different soils, across different landscapes, different countries. What was important too was the pyrolysis temperature, where we've got these lower temperature pyrolysis around 400 degrees up to 550. We were getting positive effects. When the materials were pyrolyzed at high temperatures, up to say 700 degrees, we were getting less positive benefit from those biochars. And the other point to note too, so cation exchange capacity tends to be a bit of a proxy around some soil health factors. So what it's showing here is that soils with a cation exchange capacity of below 100 millimoles per kilo, you had a greater impact than soils that had a very high cation exchange capacity. So it's kind of saying that the poorer soils, you'll get a greater benefit when you add biochar compared to an already healthy, productive, nutrient-rich soil. So yeah, from these types of meta-analysis, we can glean some indicative data around, where's going to be your best bang for your buck, where and when would you use biochar. I mentioned before, the concept around engineering these enhanced biochar formulations. So this particular one is another product that we've developed, which is an enhanced efficiency nitrogen fertilizer. So there's a lot of interest with retailers at the moment and researchers as well, and policy around the use of what's known as enhanced efficiency fertilizers. So these might be polymer-coated ureas. It might be products that come with inhibitors like ureas or nitrification inhibitors, designed specifically to lower emissions of nitrous oxide and to enhance that plant-available nitrogen content in soil. So the controlled release fertilizers are designed to better synchronize nitrogen availability with crop demand. So in most agricultural scenarios, broadacre in particular, you put your fertilizer in, you put your crop in at the start. When you've got a seedling, it doesn't need a lot of it doesn't need a lot of nitrogen. It needs nitrogen when it's that big, and that's I guess the concept of these polymer coats. So they're slow release. Everyone's used with Osmocote and other types of products like that. So you definitely get improved synchronization and theoretically lower emissions of greenhouse gas. However, the problem with many of these polymer coated, actually all of the polymer coated materials, and it doesn't matter if the polymer comes from a fossil source or from a biological source, plastic is plastic. You're adding plastic into your soil, and the estimates are sort of between 5 and 10 kilos of plastic per hectare every time these products are put into your soil, which is a problem. So, for example, many of the EU countries have now restricted the use of polymer coated materials. It's a big industry. It's worth $3.5 billion globally. Enhanced efficiency fertilizers are worth billions of dollars globally. There is definitely a need to lower emissions of nitrous oxide to improve nitrogen use efficiency, but also now with the consideration of we don't necessarily want to be adding plastic to our soil. So, do we see an opportunity here with biochar? And I think the answer is absolutely yes. So here's an example of that biochar-based slow-release fertilizer being used in a sugarcane crop, and our organisation is currently developing some paperwork to look at commercialising some of these formulations. And essentially, what we're doing now is we're coating the pore structure of the biochar with nitrogen fertilizer, and it's got a similar end release pattern to some of these polymer coated materials without actually using plastic. Biochar itself, so straight biochar, without sort of any enhanced fertilizer. So where you have biochar in your soil and you add your standard fertilizer, has shown that you get up to about 50% less nitrous oxide emissions in dryland cropping systems and 22% less nitrous oxide in paddy systems. And that's a book chapter that we recently wrote for the Biochar and Environmental Management book published in 2024. And importantly, in paddy systems, biochar also tends to lower methane emissions from those systems quite substantially as well. So, can biochar be part of this sort of $15 billion fertilizer industry? I think it definitely has got some significant opportunities there. And as I mentioned, we're having some serious discussions at the moment around looking at commercializing these products. So on to the final few slides. Hopefully I haven't gone too far over time. Oh, I'm starting to push my friendship here, I think. Sorry.
No,
but
you're
yeah,
fine, Lucas.
excellent. I've got so many topics and it's such an exciting area. So the properties of biochar. Okay, what we know is biochar's got nutrients. It's got a stable carbon content. It can have a liming effect. It's got these reactive redox surfaces. So, and I haven't had a chance to even talk about that today. So, EH sits alongside pH as an important driver of many soil chemical and biological processes. And we know that we can actually adjust sort of that redox potential in soil through the use of biochar. Biochar itself actually is a semiconductor and it can shuttle electrons. So in soil, we're actually moving electrons over millimeter scale, which is a massive opportunity to change some of these soil chemical and biological processes. Biochars have got cation exchange and a little bit of anion exchange capacity. They tend to be highly porous. They hold water. They tend to lower bulk density of soil. They can provide microbial habitat. There's been some great work out of Griffith University in the soil CRC showing that biochars themselves are actually great carriers for rhizobia, and they're being used as alternative inoculants now to peat, for example. And yeah, with all of these opportunities, we look at the right-hand side. What are the things that we're trying to fix up in soil with these biochars? It's around fertilizer use efficiency, water use efficiency, lowering leaching and gas emissions of N in particular. Yeah, can we lower denitrification? Can we lower aluminium toxicity? A ton of work in China around lowered uptake of, in particular, cadmium into rice, where biochar is put into that system. And I think that's a really important component for food safety, in particular in China, where there are many areas of contaminated soils. And yeah, we've got opportunities around long-term accumulation of soil carbon. I've only really got the one slide on soil carbon that goes into sort of any detail, and this is it. But we've got a stack of papers on this topic, and some of the work that our PhD student Zhe Han Weng did with us here at Wollongbar really is around understanding the processes of how and why biochar stores carbon in soil. Now, what's really important to understand here is that while we're adding biochar into soil, and we know how much carbon, how much stable carbon is we're adding to the soil, what we're also doing at that same time is we're increasing what's known as that soil organic carbon ceiling. So, for example, the ferrosols might have a soil organic carbon ceiling, no matter what we do with plant systems, of 4.5 or 5%. We've added biochar into that system. We increase that carbon content in soil, but we've also seen then that carbon content further increase. And that's because what we're doing is we're stabilizing new carbon inputs. So about 20 to 40% of the photosynthetic energy that plants make go into root exudates, into carbon components that are leached out of the root into the soil to feed the microorganisms to drive microbial processes in soil. When we have biochar in that system, we're now stabilizing some of those root exudates and building that new organic matter in soil. So we're stabilizing some of that new organic matter as mineral associated organic matter, and also a little bit less in the particulate organic matter. But importantly, it's that process of the interaction between biochar, the soil clay, and that new carbon that we're focusing on. And one of the numbers that we came up with is that essentially we're getting about 1 ton of new soil organic carbon, so that's newly photosynthesized material, per ton of biochar added into that system. It's important to note that's in a ferrosol. It's not going to be in every soil type. Sandy soils are going to behave really differently to these high clay soils, but there's some really significant opportunities there to build long-term, build organic carbon over the long term. And this is probably one of the mechanisms why these terra preta soils in the very first slide are actually building soil organic carbon. They're actually stabilizing that new carbon into the soil. And where's the Australian industry at? So I encourage everyone to have a good look at the ANZ Biochar Industry Group webpage. They've built a roadmap, a 2030 roadmap that talks about where biochar can fit into the Australian economy. They believe that it could become a $1 billion industry by 2030. Significant opportunities around biochar manufacture, around carbon dioxide removal, about job creation, and it also addresses 14 of the UN Sustainability Development Goals. And importantly, I think point 3 in their roadmap priority is that a standard has now been proposed, I think, to Standards Australia. Annette Cowie has been on that development committee for that standard. And I think once we have a biochar standard as an Australian standard, it will definitely facilitate, I think, many of these fairly ambitious goals. But yeah, the industry is expanding. We've got some great technology being developed in Australia, both at the biochar production end, but also now at the biochar engineering end as well, for products for agriculture. I think I'll hush up now, Camilla, and we'll go from there.
So on that note, I would like to say thank you so much.